All right, good morning. Okay, so welcome back. Hopefully everybody got a good break. Just a few words, during the long weekend, I got a few emails about the formula sheet again. Basically, I know I sent an email. I said no formula sheet, and some people ask whether I will give a formula sheet for the midterm. So no formula sheet will be provided for the midterm. Okay. Final exam, I probably will provide a formula sheet as a consistency. Okay. Yeah. So up to now, there are many new formulas. New formula means formula related to this class. If you think about it in terms of formula, so dot product vector, dot product, cross product, those are not new formula, right? Line equation for planes and equations for lines in 3D, equation for planes, so those are new, right? And it won't take you more than 1 minute. If you write 5 times, it'll be yours. Okay. The important thing is you need to know the meanings in the formula, and then you have the arc equation, scalar line formula, and so those are new. Parametric equation, that's basically how you parameterize. Those are, I wouldn't call it formula, right? Those are basically sometimes common sense, sometimes it's derived. Partial derivative, really it's not really formula, it's derivative basically. If you have known, if you're comfortable with the scalar function derivative, then you should be able to calculate partial derivative. Okay. The total differential, that's a formula which actually I will go over a little bit here again. So if you think about it, that's pretty much all the formulas you have learned so far. So there isn't really many new formulas. If there's any very tricky trigonometry needs that are involved, I probably will put it in the question, right? So you shouldn't worry too much about the formula. So let me finish one example for the total differential question, and then we'll go on to a new topic called grading vector today. Okay. So let's see, we have a multivariable function. I'll use function 2 variables to illustrate. Then what will be the total differential? So what will be the total differential of this multivariable function f of x, y? The formula-wise, basically, this is what total differential means. So total differential, basically, this is what it means. df at here equal to partial f over x. Yes. Oh, of course, running out of battery. I'll just use this one. So total differential, here's the formula. Okay. So formula basically means, what do you need to calculate? What do you need to keep it as part of the formula, right? So this thing here is called a total differential. Why is it total? Because it involves 2 variables, okay, x and y, and involve calculating 2 partial derivative. So this dx, dy, right, those are basically the symbols, you keep it. Okay, so this thing here, you need to keep it as part of the formula. And then these 2, okay, that you need to calculate. So that's the total difference formula. And now in terms of any questions, how a question involved in this kind of thing, so if you have a function given, then you just have to calculate two partial derivatives and then plug it here, and you get your total differential, right? Now in application, so when we're applying this total differential formula, we applied it differently. As I explained to several students, now this quantity, small df, the straight df at here, this is a infinitesimal small quantity. That's why it's called a differential, right? So this quantity in reality doesn't exist. You cannot have infinitesimal small quantity here. This is small, but that's not infinitesimal small, right? So in reality, you cannot have that small, infinitesimal small. So then in reality, what we have is delta f, so very small quantity. So then basically in real application, when we estimate the changes, small changes in the function f, we use this. Small changes in the function f equal to what? Equal to equal to this. So all you need to do is you change the straight d, okay, into a delta at here. Right? That's the application of this total differential formula. Okay? So we estimate. So basically here is the estimated change in function f due to what, right? And this is due to the changes in x and y. So that's what delta x at here and delta y at here means. Right? It's what's the changes in x and y. Okay. So you have a small change in x, small change in y, and then approximately how much change in the function f. So this is the formula you can use to estimate that change. Okay. So I'll show you one quick question in here, which is the assignment question. I know this due today, but might as well just to do it in here. Okay? In electronics, you have all learned basically if you have two resistors connecting in parallel, then the total resistance is this. So now the question here is, if there's this little change in R1 and R2, then what will be the resultant change in the total resistor R at here? So that's the question in here. The other part of the question is which resistor actually will be more sensitive, right? A total resistance will be more sensitive to which one of the change. So here's what we do and here. So I think the first part of the question is actually for total differential. Total differential dr equal to what? Okay. There are two different ways of solving this question. Okay. The traditional way of solving this question is you write the r, okay, into a function R1, R2 first, okay, and then you calculate the two partial derivatives and then put it into the formula here, right? Okay. So I mean, maybe I'll just use r here because this is a function here, and it's quite easy. So you can rewrite this formula to be R1 times R2 and over R1 plus R2. Right? That's the total resistance of R at here. So now, if I need the total differential, basically means dr equal to partial r over partial r1, dr1 partial r over partial r2, and dr2. Okay, that's the formula. Okay. So now I need to calculate the two partial derivatives here based on this r function. Okay. So I'll just try one at here, and then you can try the other ones. Okay. So partial R over partial R1. Where is my where's the red dot? I guess I didn't run it. Okay, there we go. Basically, you're taking derivative with respect to R1, and you can use a quotient rule right here. Okay, so here you got R1 plus R2 square. So that's basically U over V prime equal to U prime V minus V prime U, and then V square, right, over V square. Okay, so U prime V. So U prime in here, meaning this is U here, is the partial U over partial R1, which you got R2 times V times R1 plus R2, and minus V prime times U. So partial V over R1, which is 1, times U, which is R1 R2. Okay. Good. So that's the results of this partial derivative, and a little bit of simplification, you get R2 square over R1 plus R2 square here. Okay? Yeah. Then from here, I guess the answer simplified a little bit. You can stop here, which is nothing wrong. Okay, this is basically the answer here. But I guess in the answer, in the solution I provide in the assignments, okay, we used this expression of R at here. Okay, if you look at this one, if I R square, which is what, R1 square R2 square over R1 plus R2 square. So that's R square. And then basically means this partial derivative, if I involving this R at here, which basically I have a R square at here, and get rid of the R1 square. So that's basically the simplified expression for this partial derivative, right? So this whole chunk divided by R1 square, you get back to this here. Okay. So all you need to do is plug it over here, right? And then calculate the partial R over R2 and plug it here, you get your dr. Okay. That's total differential. Alright? Yeah. Now second part of the question is R1, okay, will go through certain changes. So in this question, you need to read it carefully. Basically, you need to know what's the initial value and what's the final value. Okay. In this case here, the R1 says it goes from 20 ohms to 20.1 ohms. Okay. Okay, that's the description. So starting with 20 ohms and ends with 20.1 ohms. And R2 starting from 25 ohms and end up with 24.9 ohms. So always remember, right, here is your starting point and here is the end value. Okay? Okay, so what is the starting value? What is the end value? Because you need the two information to calculate your delta change. Okay, your delta change in the R1 and R2. So our end starting value is 20, and end is 20.1. So you always use the end value minus the starting value. So 20.1 minus 20.1, and here is 24.9 minus 25, negative 0.1. So always use the end value minus the starting value. Okay, so that's the trick at here. So once you find these two, then our estimated change, delta R, will be approximately, okay, your partial R over R1, that partial derivative, times delta R1 plus this right here. Okay, that's how you use to estimate the changes, right? Estimate the changes. So I can plug in the delta R1 with 0.1. I can plug in the delta R2 with negative 0.1. What about these two partial derivatives, right? Then the two partial derivatives basically, after calculation, you can see the two partial derivatives are basically function of R1 and R2 again. Okay. Then what you do with this one here, I'll just write down this separately. You basically substitute this R1 with initial value. I'll write using words here. And R2 initial value. Okay. The two initial values of R1 and R2, put it into the function of the two partial derivatives here. So remember, this is initial value here. Okay, so I'll call it starting value. Let's call it initial value here. Okay. Those are initial values. So if I look at my original function here is here, R2 squared over R1 plus R2 squared. So initial is 20. So here R2, let me write it down again. Plugging 25 at here, and R1 plus R2, and 25. So those are initial values, right? And now you can calculate what this value is, and then plug it back over here. Similarly for this partial derivative. And then also plug in delta R1, delta R2. So that's the typical procedure for making use of this total differential to estimate the changes of a certain function f, okay, given a changes of the variable, right, inside the function f, okay, R1, R2. So I'll leave the calculation for you to do it, okay. And all you have to understand correctly in this case here is how to calculate delta values, right, using the end value minus initial value, and how would you substitute the initial values into this partial derivative results, okay, to do the proper calculations. Okay, yeah. So that's it for partial derivative. Okay. Any questions so far? Yeah. There won't be any lecture on Thursday, right, but I will be available in the office during the lecture time, of course. But outside the lecture hours, I should be there if I don't have any meetings. Feel free to come if you have questions, all right? Yeah. But otherwise, remember Thursday nights, 7:30 to 9 o'clock. So our exam is in Arts 366. Okay. All right. Let's continue on the new topic now. Grading vector. This is not part of the midterm, okay? So let's look at what is grading vector and where is it coming from, what's the definition basically. Okay. Let's consider a function of three variables right here. So let's say I have a function w involving three variables x, y, z. Incidentally, each one of the variable, okay, suppose that, okay, they are a function of t. Okay. And then I'll use this. Let's see if I'm gonna calculate the derivative of w with respect to t. I can use the chain rule as we learned in the previous lecture. So chain rule basically saying you had to calculate the partial derivative w with respect to x first. So let's use f right here because I use f right here. So partial f over x first. and then dx over dt, partial f over partial y, dy over dt, partial f over partial z, and dz over dt. Okay, so that's nothing new. That's basically the chain rule for the partial derivative. So you can consider this x of t, y of t, z of t. You can consider this as basically a part of the parametric equation, right? So that can be part of the parametric equation. Now, for this one here, I'm going to separate into two terms. So you can see I have a term here, and a term at here, and then you have three derivatives at here, right? Three derivatives, and these three derivatives are basically the derivative of this parametric equation, or dr over dt. Okay, so if I take a dr over dt, you get these three things at here. So I can separate this single expression into into a dot product between two vectors. So if I define a vector which consists of three partial derivatives, another vector which is basically this dr over dt. Okay. So this is essentially dr over dt. And this one here, now this is something new. Okay, this one here has three partial derivatives as part of the vectors at here. So what we do is, and this is where we're going to define this vector as a new vector here. And the way we define it is this. We define it as this. This is not a triangle, this is an inverted triangle here. Okay? So this symbol here is called del. It's called basically, it's called del at here. So to pronounce it properly, called del f. So del f is defined as the vectors which consists of its first order partial derivatives. Okay. And this vector here, okay, is basically what we call the gradient vector. Okay, so it's a gradient vector. You know, when you draw a vector, you always draw a vector essentially somewhere. In this case here, more precisely, it's a gradient vector at a certain point x, y, z, because you can always plug in the actual x, y, z coordinates into that vector to get an actual vector, right? So that's gradient vector. How you get it is essentially calculating three partial derivatives and then put it into the vectors. So if you recall that journey, remember that df over partial f, and now we see this del f. Okay. So there were a lot of these operations involving all three symbols, okay, for the rest of the classes. Okay. So this del at here, okay, just like so this del at here, okay, just like the street D, okay, it's an operator. It's basically a differential operator. Okay. So operator basically means the del itself, okay, is actually defined as partial over partial x It's a derivative. It's, of course, here it's partial derivative. Okay. And del itself, it's a vector operator. So Operator basically means if you apply this operator to any function, right? Let's say you have a derivative operator. I apply this operator to a function, you got a derivative. Okay? You got an integration operator, then you apply it to a function, then you got an integration. So if you apply the del operator to, let's say, any function f, okay? If a function f is a 3 variable, then you get exactly these 3 things here. Okay? So of course, if a function is just 2 variables, then you don't have this term, just the first 2 terms. So that's how you use operator in here. But bottom line, the difference is here. This is a vector here. This is a vector operator. Okay? And operator, you can also think of it as a sort of like a system. And bottom line is, okay, this is a linear operator. Okay, it's a linear operator. Just like the derivative, it's a linear operator. Okay. And in 246, you're learning system dynamics, and the definition of a linear operator or linear system is basically means what? Meaning you need to satisfy the so-called superposition rule, right? So if I have, let's say, a constant times a function c1 times a function f, I have a constant times another function g, and if we apply this operator to this whole chunk right here, the superposition rule basically says this. Okay? That's what linear operator basically means. Okay, so mathematically you can see that grading vector is very, very simple. Okay? All you need to calculate are 3 partial derivatives. That's it. And then you put it into the vector format, you get your grading vector. So mathematically, the computation-wise, very straightforward. Okay, very straightforward. Now, the trick, of course, is what does grading vector mean, right? So I won't be able to show you a proof for now, and after the next lecture, directional derivative, I'll be able to show you a proof. So, but before I tell you what grading vector means here, so let's take a look at, just get some superficial feelings with some computations, okay, through an example here. Okay. So let's use the function 3 variables to illustrate the computation. So here's the function 3 variables, and we wanted to calculate the grading vector of this function, and also the grading vector at a specific point 1, 1, 1. Okay, 1, 1, 1. So let's calculate this using the formula we have just defined. Okay, so that's what's going to happen. So we need to calculate 3 partial derivatives. So let's take a look at the 3 partial derivatives. What are they? First partial derivative is back to x. Then you treat the y and z as constants. We got 2x out of here from the first term. And from last term, you got z over x out of here. Okay, that's the first partial derivative. Second partial derivative is back to y. That's a simple, just 2y, because all the other terms has no y there. So just this term has a y here, y squared. Last partial derivative is back to the z. And you have a z over here, so negative 4z. And there's a z over here, so ln x. That's it. That's basically the grading vector. Okay, the grading vector. So the last step, we calculate this vector at 1, 1, 1 point. Okay, this vector at 1, 1, 1 point. All you need to do is substitute x equal to 1, y equal to 1, and z equal to 1 into these grading vectors.
And we got 2 times 1 plus 1 over 1, 2 times 1, and ln 1. And this is simple, so that gives you 3, 2, negative 4. So that's essentially what computation, right? What's the kind of computation involved right here for grading vector. Okay. So as you can see, if you need to calculate grading vector, really no mystery at all, right? You know, it's just simple calculation to 3 partial derivative and involving substitutions if necessary. I'm going to illustrate how you can properly sketch the grading vector. I'm going to use a 2D function to illustrate. Okay. Yeah. Let's take a look at this example. So I think I'm going to skip this this one here. But anyway, let's try this one. Okay, let's try. Look at this. Look at this function here. Z equal to f of x, y equal to x squared minus y squared. Okay. So in when I started the multivariable function, I think I showed you this function. And this is, if you recall, that it's a saddle. I give you a saddle face, like a horse saddle. So let's see if I calculate del f, okay, which is partial f over partial x and partial f over partial y. Okay. So we get 2x negative 2y. Okay. Similarly, if I wanted to calculate, let's see, okay, this grading vector at 1, negative 1, okay, then all we need to do is plug in the 1, negative 1 into this grading vector. You get 2, negative 1, 2 multiplied by negative 1 is 2. So 2, 2. So that's the grading vector at 1, negative 1, okay, for that particular grading vector. So how do I basically sketch those grading vectors thing, right? So first of all, maybe I want you to observe at here, okay? Yeah. Let's just observe these 2 examples. For the first example here, I have a function of 3 variables. Then we calculate the grading vector. So tell me what's the grading vector here? 1, 2, 3. It's a vector in 3D space, right? Okay, that's because this is a function of how many variables? It's 3 variables, okay? So you end up with a basically vector pointing in the 3D and in some direction. Now this one here is a function what? 2 variables now, right? And then you calculate the grading vector. You look at the grading vector here. So when you have function 2 variables, its grading vector is a 2D vector. And then you plug in certain value, you got a 2D vector. 2D vector essentially in this case here, we're talking about x in the xy plane. So for example, right, if I look at this one here, how do I sketch this grading vector 2, 2? Now this is x, this is y. If I give you just a vector 2, 2 and ask you to sketch this vector, and you're without telling you anything about the grading vector, right? Just say, okay, here's a vector 2, 2. Can you sketch that? So what would you do? You basically go to xy plane and you find, okay, here's a 2 and here's 2, right? And find the coordinates 2, 2. Right? That's 2, 2 coordinates. And then you create what? You create a vector from origin to that point. So this black one here is 2, 2. Okay, that's the vector. However, when it comes to sketch for grading vector, okay, your starting point of the vector is not origin. So your starting point is always the actual coordinates where this 1, negative 1 is. So basically, in this case here, where is the 1, negative 1? So x is 1, x is 1, y is negative 1. So basically, here is 1, here's negative 1. Okay. So this is basically where you compute you calculate your grading vector. You substitute these coordinates into here to get to 2. That makes sense? Right? So when sketching the grading vector, so what happens is you need to move this black vector here, which is 2, 2, to start from 1, negative 1. And then you're not going to change the direction, you're not going to change its magnitude. All you need to do is to change its starting point. Yes? Yes. So x is 1, y is negative 1. That's... Sorry? Oh, sorry, of course. What am I talking about here? Yeah. One is here, right? Yeah. Okay, here is our starting point. And let's draw it here. So we're not going to change its direction, we're not going to change its magnitude. All we do is we move the vector, okay, parallelly over to this starting point here. This is 1, negative 1. Okay. That's how you draw a grading vector. So technically speaking, if you think about it, right? If I have this function here, and I calculate the grading vector, if I plug in this x, y with different values or different coordinates, I will end up with an infinite number of actual vectors. So that's how you actually visualize this so-called, in the next few lectures we'll call it, the grading vector field. Okay, grading vector field. You draw all the vector out, you get a field of vectors. So that's how this looks like it here. So this is that saddle surface. Okay, this saddle surface. And then if I draw out all of the grading vectors, okay, you can see with the appropriate direction and appropriate magnitude representing the length. And here's the fields of vectors you will see. This is blue one. Here is the grading vector field. Okay. And later we have a basically genre called the vector field. Okay, but in this case, this is a grading vector field because it's generated from the grading vector. Okay, yeah. If you zoom it in a little bit here, let's see if I try to find the 1, negative 1. Where's x here? I'm not sure actually. Maybe this is x and this is y. So 1, negative 1. If you zoom it in here, and then somewhere up there, so you'll find the vector essentially, like what we just draw here. Okay. Yeah. The lecture notes give you some examples how to plot these things using MATLAB code. I'll show you another one here, okay, just to emphasize. I think it's important now to get a feeling of what grading vector is. Let's try this one here. Z equal to f of x, y equal to x squared plus y squared. So this is a paraboloid. A very typical surface that we will deal with in our lecture here. So for paraboloid, okay, it's basically a bow pointing upwards, and that's your z equal to f of x, y. Okay. So let's take a look at. I call it the first case at here. So I'm gonna calculate a grading vector as this. So del f, okay, at 1 point. So 2x 2y at 1 point, which is 2 2. Good. Okay. So that's grading vector. Now this time I'm going to sketch the gradient vector, okay? But not only sketch the gradient vector, I'm going to sketch an additional curve, okay, to put them together. And this additional curve, okay, involving basically the so-called level curve. So let's take a look at this particular coordinates 1, 1. If I find the 1, 1 in here, let's see, this is 1, this is 1, here is 1, 1 point. Right, here's 1, 1 point. So at this particular 1, 1 point, if you go up to the surface, okay, and that's going to give you a z value, right? Okay. So the z value, okay, will be, so z at 1, 1 will be what? So plugging 1 and 1 in here, you got a z equal to 2. Okay, you got z equal to 2 here. So now if I slice this surface, okay, slice this surface at here with, so here is 2, with a plane, okay, z equal to 2. So if I slice this whole surface with a plane equal to 2, then what I'm going to get is, so you're going to get, in this case, you're going to get a circle, right? You're going to get a circle. Basically, you're plugging 1, 1 here, you get a z equal to 2. If you slice this one here with z equal to 2 plane, you get a circle, and that circle is 2 equal to x squared plus y squared. Good? Yeah. So basically this circle has a radius of square root of 2. So now I'm going to do is I'm going to drop this circle, okay, drop the circle into this xy plane. That's how we essentially graph the so-called cluster of level curves. So if I drop this circle to the xy plane, and that circle will pass through this 1, 1. Okay. That's the circle in the xy plane. Same circle basically, just drop it into the xy plane. Sound good? Okay. So now I'm going to sketch this gradient vector now. Okay, sketch this gradient vector. So let's look at how we sketch the gradient vector. Remember, when you sketch the gradient vector, you don't sketch the vector, just the vector 2, 2. You sketch the vector to start from whatever that you plug in the values are, right? Start from 1, 1. So here is 1, 1 here. You sketch a 2, 2, that's actually easy, you know, basically if I plug a 2, 2 here, and then 2, 2. In this case, starting from 1, 1, you draw a vector, that's the direction. It's exaggerated a little bit. If this is 2 here, this 2 here. So that magnitude, right, represent a little bit too long, I guess. Okay. So that is, this one here is in the xy plane. Okay. So this is your del f at 1, 1. Okay. It's in the xy plane. Starting from 1, 1. And at the same time, that level curve goes through the point 1, 1. Okay. So I'm putting two information in here because may not be used for now, but it will be useful for maybe next lecture. Okay. Yeah. Actually, I will show you one thing shortly here. Basically, this gradient vector I'll show you is this gradient vector is perpendicular to that circle. Okay, to the circle here. Well, which actually makes sense. Basically, if you look at this green vector here, if you extend the green vectors, it will go through the origin, right? It will go through origin. It's if I look at it from the top here, this is xy plane, and this is your circle. Okay, square root 2 as radius, and then it's not very good coordinates, and then here is that green gradient vector del f, right? There's a gradient vector del f. So this del f pass through the origin here, okay, and I will show you this is perpendicular to the circle, which actually I don't need to show you because I will prove it, but in this case it's very obvious, because when you have a reading lines, okay, going out of this origin here, and this is a circle here, that reading line is what we call it's perpendicular to this circle, okay, to the circle. So in this simple case, function 2 variable, I sketch a grading vector which is a 2D vector. So this is an illustration again. If I zoom in a little bit here, so you can see if you have a whole bunch of level curves and your grading vectors, right, they are all essentially like readings of arrows pointing outwards. At the same time, it is essentially is what we're going to show you is perpendicular to that level curves at here. Okay, so all of the grading, each one of the grading vector is perpendicular to that level curves. Okay, so that's a simple example here, okay, for this case. So now I need your attention. So I'm going to change this. I'll use the same function, but I'm going to change to a slightly different perspective now. Okay. Yeah. So this is what I call the case number 2. Okay. Same function, but then this time I will define a different variable . So I'm going to define a w equal to z minus x squared minus y squared. So this absolutely looks different from that z equal to x squared plus y squared now, right? So this essentially it's a function of 3 variables now. However, okay, if I let w equal to 0, so what do I get? I basically get back this z equal to x squared plus y squared. Yeah, as simple as that. Okay. Now, if you recall, when we learned multivariable function, and I have repeated many times, I said if you have a function of 2 variables, okay, like this one here, you can certainly sketch out in a 3D space. If you have a function of 3 variables like this, w, okay, you can sketch in 3D. Okay, you cannot sketch in 3D, maybe 4D. Okay, but if I still want to visualize this function 3 variable in 3D, then one way to do is what? Is to let w equal to a different constants, and then plot out each. Once you let the w equal to a constant, for example 0, then you end up with just function 2 variable now. So you can sketch that as a surface. So this is basically what we call level surface, right? It's called a level surface. So if you let w equal to a different constant, you will get just a slight different surface. It's like moved up surface. Okay. So for example, if you let w equal to negative to 1, then you get a z equal to x squared plus y squared plus 1. So the only difference between the 2 level surface, they move up in the z-axis direction by magnitude of 1. Okay. But what I wanted to show you now is, see, previously we calculated the grading vector here is del f, which is function 2 variables. Now this time I wanted to calculate del w, which is function of 3 variables. Okay. So del w. So what is del w then? That's partial w over partial x, partial w over partial y, partial w over partial z. Now let's look at this function, which is w is z minus x squared minus y squared. So partial over x, negative 2x, partial this here, negative 2y, and partial of that is 1. Okay. Good. So similarly, let's say I wanted to find out the greeting vector at a certain point. Let's see, 1, 1, 2. Plug 1, 1, 2 into the del W. So 1 over here, -1, -2, 1 here, -2. And Z is already a constant, so it really doesn't depend on anything at all. So you basically use the 1 here as it is. Okay, that's the greeting vector, the W, del W, at -2, -2, and 1 and here. Okay, and 1. So how do I sketch this greeting vector then, right? How do I sketch this? So remember this greeting vector here, okay, comes from the calculation, okay, based on, you can consider this is based on a level surface z equal to x squared plus y squared. Then to demonstrate this greeting vector here, what we can do is, let's plot this z equal to x squared plus y squared first. So plot this surface first, which is a paraboloid. Okay, so plot that surface. Okay. And this surface here is basically w equal to 0 or z equal to x squared plus y squared. So now I'm going to plot this vector now, -2, -2, and 1. Okay. So first, let's just plot -2, -2, 1. So if this is x-axis, this is y, this is z, and x is -2, y is -2. So this is -2 here, and here is -2 here. And let's say this is 1 and here. Okay. And it's a little tricky. Okay. So you have a vector pointing inwards, right, into that corner. So -2, -1. So that's the actual vector. Okay. This is the actual vector for this based on -2, -1. However, when you draw the greeting vector, remember, we have to start the greeting vector from the actual location. In this case here is 1, 1, 2. Okay, so 1, 1, 2 is the actual location. So 1, 1, 2, where is 1, 1, 2? So now here's 1, and then here's 2. So 2, if you see, this is x, y, z, right? If you look at this surface we just draw here, if you plug 1, 1 here, you basically get 2 equal to 1 plus 1, right? Yeah. So the 1, 1, 2 in this case here happen to be right on this surface, z equal to x squared plus y squared. Okay, so here, let's say this is 2 here. This is the point. This is the point 1, 1, 2. Okay, that's 1, 1, 2 here. So then all you need to do is to bring this original -2, -2 vector up to this location, and then draw it, okay, to the same direction, same length, but starting from 1, 1, 2. Okay. So that's how you plot this greeting vector. So in this case here, just like the previous case, I plotted a level curve and a greeting vector. In this case, I plotted a level surface and the greeting vector. Okay, so two things at the same time. So level surface and the del W, okay, together. As I'm going to show you, this del W here is perpendicular, okay, to this level surface. Okay, just like the other case, the greeting vector is perpendicular to the level curve. In this case here, this greeting vector is perpendicular to this surface at here. I'll show you shortly, okay? Yeah. So a lot of question mark. I put some conclusion here, but I haven't answered the question mark here, okay? Yeah. But for now, I think you need to be clear is if you're required to sketch out roughly a greeting vector, you need to calculate it first and then draw the vectors to start from the actual location where you did the calculation. Okay, so that's the proper way of drawing a greeting vector. So let me make a conclusion first, and then I'll show you why this. So let's call it the comments here. Okay. So what is the geometric meaning of gradient vector? Okay, the geometric meaning of gradient vector. I won't be able to provide a proof for now for these comments. I will give you a proof after next lecture, directional derivative. Okay. So here is the conclusion here. Okay. So gradients of function f. Okay, so gradient function f, or gradient vector of f. Okay, of function f, okay, has two meanings. Number one, okay, first of all, when you have a vector, first we had to understand this is a vector. When you have a vector, what are the two information associated with the vectors? Magnitude, direction. So let's talk about direction first. The direction given by this gradient vector points to the direction of the greatest increase of function f. Okay. So that's very important information. So this gradient vector, which is del f, give you a direction which points to the direction that indicates the greatest increase in the original function f. Okay, so I'll explain it a little bit. And then second of all, okay, this is the direction, the information that the direction gives us. The second of all is the magnitude. The magnitude of del f, right? This is the gradient vector. The magnitude of this gives the rate of increase. Okay, the rate of increase. So, the first comments here is, okay, so the direction tells me if I go this direction, then I will have the greatest increase of this function f. Fine. But then the second part of the question is, so what's the rate of change? How fast does it increase? The magnitude of that gradient vector will give you that information. Will give you this rate of increase here. Okay, yeah. So that's the conclusion regarding the gradient vector. For example, right? Let me show you this through here. If I have a paraboloid here, if I got a paraboloid, okay, and if you have a point inside xy plane, okay, you have a point inside xy plane here. So let's say this is your starting point. Okay, if this is a starting point, let's put a starting point here. Okay, let's put a starting point somewhere inside here. So the natural question is, if you move up these points, okay, so that point corresponding to a point on the surface, right? Okay, then suppose that you have a friend is trying to climb the mountain, and you are his best friend on the ground here, okay, trying to help him to climb the mountain. So your friends will ask you, hey buddy, which direction should I go in order to apply to the tops of the mountain as quick as possible? So you're right here, right? So then you have to give him some information, good information. So then you look at it, let me calculate the gradient vector first. And then you calculate, say, okay, that's that direction. Go that direction. Okay, go this direction. Then he will climb up right, in that direction. So that's basically the idea. And then if he asks you, so how fast am I going to climb up? You say, okay, let me calculate the magnitude of this vector. That's how fast you will climb up. Okay, yeah, that's the idea of a gradient vector here. This is a 2D, right? Excuse me. So I always like another example trying to illustrate the idea here. So let's say you have a magic oven here, right? So the magic in here is you can punch in the coordinates, and then the device will spit out a grading vector. Yeah. So you're cooking this the dough right here. You want it to cook it as fast as possible. So, and you place the dough somewhere inside the oven. Okay, and says okay 352, right? And how do I know that I can cook it as fast as possible? Then I had to place that a place that has the highest temperature, basically. So the oven says, give you this gradient 345. So what does that mean? Basically means let's move this guy. This dough right here in a direction 345, starting at here 352. So move it somewhere in that direction. Okay, and if you move it that direction, but see, you don't move it all the way to the direction. You just move it a little bit off from the initial 352, right? Just a little bit off. And then you move it to somewhere else again, and you look at the new results spitting out from the oven, and you move it again. So maybe a little bit different direction now, until it's at the highest temperature. Okay. As a matter of fact, at the highest temperature, the gradients at here, you can take a guess. What would that be? 0. Okay. So that's the idea of this grading vector set here. Okay. And we're gonna be able to actually prove what I just write down the comments in here after finish the directional derivative. Basically, the y is, why does it point to the direction gradient increase? Okay, and this one here, after our directional derivative, we'll be able to provide a proof. Okay, called directional derivative. Good. Okay, so now I'm going to tie up the other two loose ends. Okay, remember I mentioned about the gradient vector perpendicular to the level curve, and the other gradient vector in 3D is perpendicular to the level surface. Okay, so this is what I wanted to prove at here. Very simple proof. So two theories. Let's say the first one here. Given a differentiable function z equal to f of xy, so it's a 2D function in here, then here's the conclusion. So the del f is perpendicular to level curve. Level curve essentially means you slice the surface with an arbitrary plane z equal to c. So that's what level curve looks like. You substitute a z with a constant c, you get a level curve. This is equivalent to c. Okay, so equivalent. It's equivalent to c. The del f is perpendicular to a tangent line of this level curve f of xy equal to c. Okay, so equivalent to c, it's like that. What this means basically, here's what I will going to try to prove at here. So let's say I have a level curve, and this is your f of xy equal to c. Can be a simple circle, can be any arbitrary shape, right? So here's the level curve. Now, if we plot out our gradient vector del f, and we'll be able to show that this particular vector is actually perpendicular to the tangent line, okay, at that point. So this tangent line is the line tangent to the level curve. Okay, so this is a tangent line. And that's what we equivalent can see, that this gradient vector is perpendicular to this level curve. Okay. All right. So how do we prove this? How do we prove this thing here? Okay. Because this is a curve. Okay. So I'll consider using what we learned here. Consider this curve using a parametric equation. So just temporarily, I'll consider this curve as can be represented using a parametric equation, R of t. So now I can change this description. If I want to prove that del f is perpendicular to this tangent line, alternatively, I can try to prove that this grading vector is perpendicular to what? To a vector tangent here. And a vector tangent here, as we learned, the velocity or the derivative dr over dt, which is naturally a tangent vector, right, to the point, at the point to the curve. So all I need to show is whether the del f is perpendicular to this dr over dt or not. Okay, that's what basically I want to show. So let's start from this level curve. Here's the level curve here. Okay, f of x, y equal to c. Since we're representing this level curve using the xy using this parametric equation, so I can replace the y of x, y here with the parametric equation x of t, y of t. Okay, so you plug in your x of t, y of t into this function right here, which is supposed to be maintaining the same thing, equal to c. Then I will take a derivative of both sides, okay, of this equation here. So take derivative with respect to t for both sides of this equation. The right side seems to be pretty straightforward because the constant and derivatives must be 0. The left side here, that involves basically the partial derivative and the chain rule partial derivative. So you get partial f over partial x, and then dx over dt, partial f over partial y, and dy over dt. Yeah. Okay, so that's the derivative of the left side here. And now I'm going to rewrite the left side, okay, into the dot product between two vectors. Very much like what I did at the beginning of the lecture. Okay. All right. So now you can see we have the first term, which happened to be the grading vector, and the second term, which is what? The derivative of the parametric equation, or that level curve. So you got essentially the grading vector dot that derivative of the parametric equation equal to 0. When you have two vectors dot product 0, means the two vectors must be perpendicular. Okay, so you get del f perpendicular to this here. Okay. So that proved that what with the conclusion here. So this grading vector must be perpendicular to a line tangent to the level curve at that point, or the grading vector is perpendicular to the level curve. Okay? Yeah. Yes. Here.
From the column, we said the del f is the direction of graded increase of f.
Yes.
So, but how do I tell del f is I cannot visualize it.
Yes. So that's a very good point. At this stage, I find basically that's a very common thing at here. So let me go back to this here. Okay, this is basically the example we've gone through. Now, the grading vectors drawn relatively and together with the level curves. When we see the gradients increase the function f, it's the function f here is this. It's that surface. This is your function f, f of x, y. or it's z equal to f of xy. Okay. So you can consider here, if I here I'm just showing you it's just a level curve, right? Where is that function f of xy? It's actually on the top of it. It is a planar, but it's on the top. There is a surface. Okay, there is a surface here. Whenever you pick a point x, y on that surface, there is a z value, right? So the question is, how fast the z value will go is given by the del f information. Okay, so your actual surface is actually on the top of it. Okay, not this one. This is your level curve. Okay, this is the level curve here. The surface, it's this. Okay, this is the surface here. Is that good? Yeah. So let's continue from here. Okay, so we proved this now. Let's consider the other second case here. Okay, given a different function. Now this time it's a function of 3 variables. And then we can show that this del f is perpendicular to level surface f x y z equal to c. Okay. Equivalently, we can see that this del f is perpendicular to a tangent plane, okay, of this level surface. Okay. That's 2 equivalent statements. So let me show you what does it mean here. Okay, show you what does it mean. And I really want you actually try to this one to distinguish the meaning between a 2D grading vector and a 3D grading vector. And what does that relates to the comments, relates to the conclusion, and what does that greatest increase means, right, for a 2D and a 3D case here. That's, if you can visualize that properly, you basically understand the grading vector properly now. So let's consider this one here, show you a quick proof at it here. Okay. Level surface is f of x, y, z equal to a c. Essentially, you let the w equal to a constant, then you get a surface. Okay. And I'm going to plot this level surface just as arbitrary level surface. Let's say, for example, I have a surface here. Okay, so this is my level surface. Okay. And then if you pick a point, okay, which is right on the level surface, so this point has x, y, z here. Okay. Then you calculate, let's say, the gradient del f. So the calculate gradient del f here is partial f, partial x, partial f, partial y, partial f, partial z. 3 variables, right? So 3 vectors, vector of 3 components here. Then del f will be somehow, okay, give you a direction, del f like that. And we wanted to prove that this del f is perpendicular to this surface, to this level surface. Or equivalently, this del f is perpendicular to a tangent plane at that point. So let's see if I draw a tangent plane, okay, to that point. And that's what we want to show, that del f perpendicular to the grain plane. So how do I prove it then, right? Here's how we can prove. I'm going to sketch a curve. Okay, so this is a curve right on the surface. So this black curve here is a black curve is a C. So let me call it R1 of a T. Okay, it's an arbitrary curve I sketched, okay, along that surface, level surface, and passing through this x, y, z. So I call it a parametric equation. Let's say R1 of t here. Suppose it has x of t, y of t, and z of t, okay, a set of a parametric equation. Okay. So now I will try to prove why this is the perpendicular relationship now. Okay. Start from your f of x, y, z equal to c, starting from this equation here, level surface. And then we're going to take derivative of both sides of this equation. Very much the same approach as we showed the perpendicular relationship between the del f and the level curve. The right side is constant, so derivatives must be 0. The left side, we use the chain rule, so partial f over partial x, dx over dt, partial f over partial y, dy over dt, partial f over partial z, dz over dt. Chain rule. Then we separate this into 3 components into the dot product of two 3D vectors. Okay. There we go. So you look at these two dot product here. The first term is basically the gradient. Right? The first term is the gradient. And the second term is the dr over dt, or dr1 over dt in this case. Okay, there. Dot product equal to 0 means this del f must be perpendicular to this vector dr1 over dt. Okay. So getting back to that drawing it here, right? Remember the black curve is an arbitrary curve on that surface, on that level surface. Then dr1 over dt must be basically a tangent vector over here. Okay, at that point. So what we just showed is, doesn't matter which curve. I can draw arbitrary here. I can maybe draw a different one. Let's say I can draw a different one at here, which is also a curve on that level surface. As long as it's a curve on the surface, okay, you draw a tangent vector over here, okay, for that particular curve. That del f will always be perpendicular to the tangent vector. Okay. So you can try to visualize. Here is a surface. Here's a particular point, and then here's a gradient vector. And then at that point, you can draw any tangent vectors. Okay, any tangent vectors. Then any tangent vector to the plane, basically now. As long as it's a tangent vector, then the del f must be perpendicular to that vector. Okay, that's basically what we just proved. And that naturally basically means, you see here, so what plane contains all the tangent vectors? So that's a tangent plane. If you draw a tangent plane, that plane contains all of the tangent vectors. So basically means the del f must be perpendicular to the tangent plane at that point, okay, to the surface. So that's this second part of the equivalent statement. So it's perpendicular to the tangent plane of the level surface. Okay, yeah. Okay, so we're running a little time here. I'll show an example in the next lecture here. Okay, how to find a tangent plane given an arbitrary surface. Okay. Any questions so far? So good? Great, thank you.
I have a question about the midterm. Are we
Sure.
expected to know